what the L does the Drake equation have to do with climate change? Back when I was a kid, catching alligators on a lake in Florida and watching the Saturn V rockets go up from my backyard, Frank Drake, Enrico Fermi, Carl Sagan, and a lot of others started speculating about the chances of finding radio signals from intelligent life elsewhere in the universe. Today, I'm a carbon cycle guy and climate guy at NASA studying life on Earth. I'm going to go through the terms of the Drake equation very quickly, talk about what some of the how the probabilities have changed. R sub star is the rate of formation of stars suitable for life. F sub p is the fraction of those that have planetary systems. N sub e is the number of planets that per solar system that have a suitable environment for life. Now, when Drake and his gang debated these terms, and for many decades afterwards, there were no known planets outside our solar system. Today, because of the Kepler mission, there are over 3,000 planet candidates and over 1,000 confirmed planets. So we now know that the terms of the Drake equation, these first terms, imply a large number of planets in the universe, billions and billions of planets, where life might occur, confirming Drake's and Fermi's and Sagan's intuition. Now, F sub L is the fraction of suitable planets on which life actually occurs. Now, we know, or we have evidence that on Earth that life appeared as quickly as 500 million years after the formation of the planet, which is really fast. My friend Bill here is standing on fossilized stromatolites that were left by the cyanobacteria, which were the first organisms to begin transforming the atmosphere of the planet from mostly nitrogen and carbon dioxide to mostly nitrogen and oxygen. But it wasn't until about 500 million years ago that multicellular life proliferated. So finding any kind of life elsewhere in the solar system, on Mars or Europa, would be mildly interesting. Finding life based on lipid bilayers and nucleic acids would confirm the panspermia hypothesis for the origin of life. But finding life that was based on some other sort of chemistry would be truly transformative for our notions of biology. Either way that it would that would work, it would imply and improve the chances of life appearing elsewhere in the universe. Now, I want this next. There we go. F sub I is the fraction of life-bearing planets on which intelligent life emerges. So what about intelligent life? If we search the universe, will we find it? Maybe not. But seriously, how will we recognize intelligent life if we find it? If we found life swimming in the atmosphere of Jupiter that was singing ballads across thousands of kilometers, would we call it intelligent? What about a tentacled race that could solve complex 3D puzzles? Or a quadrupedal race that could seemingly read our minds and interpret our emotional state? The fact that several arguably intelligent species exist on Earth besides ourselves implies that argues for the evolution of intelligence once multicellular life appears. But F sub C is the number of these civilizations that are using technology the way humans have for the past 150 years or so. And that's really what this equation is solving for. So let's do a Bayesian reevaluation of our prior assumptions, modified by what we've learned. We know that these first terms are very, very large. And we know for certainty that these others are non-zero. And yet, n continues to be 1. Now, this implies that L, the length of time that civilizations emitting radio signals exist, is perhaps very, very small. So my prediction is in the next 50 years, we will better constrain the value of L, whether or not SETI detects alien radio signals. It may be that the length of time that civilizations release detectable signals is short because they embrace efficiencies that reduce the wasteful electromagnetic radiation and the consumption of resources that disrupt climate. But consider this, early climate models that Carl Sagan used to show that a nuclear exchange between Soviet Union and the United States could induce a nuclear winter was something that was high in people's minds in the early 1980s. But today we face an insidious, slower moving threat. At NASA, we do research that shows that human emission of carbon dioxide is disrupting climate in an unequivocal way. So we know that it is essential that the U.S. and other nations work together to eliminate carbon emissions. Otherwise, we will constrain the value of L to be very small.